Hello everyone, my name is Benson and today I'm going to present our work on Viper, an efficient hybrid PMem-DRAM key value store. So let me start off by quickly introducing persistent memory. Persistent memory, you can see here DIMM on the left hand side by Intel. It's a new storage technology that sits somewhere between DRAM and SSD in the storage hierarchy. So this means it offers speed and byte addressability known from DRAM, but also capacity and persistence known from SSDs. So it's somewhere in between there. And these characteristics actually have the potential to dramatically shift how storage systems interact with persistency in the future, which is why we're really interested in looking at this for storage systems. So why do we want to look at PMem for key value stores? First of all, so key value stores have really become a fundamental storage layer in many applications in recent years. And they're really heavy on raw I/O, so there's not a lot of processing logic. It's a lot of just I/O to persistent storage. And lastly, key value stores are really performance critical in many applications. So this is really a sweet spot to test and validate this new storage technology to see how can we utilize it to improve storage layers. We decided to build Viper, a key value store with PMem, and it's an embedded key value store. So there's no client-server interface, no network, but it's an in-process database like RocksDB or Faster that some of you may know. So when building Viper, we basically have three core design choices that we came up with, which are direct PMem writes, page-aligned storage segments, and the uniform thread-to-DIMM distribution, all of which are relevant to achieve the performance needed from persistent memory. So I'll go into these in detail in the next few slides. So the first benchmark we ran was actually a small sequential versus random write benchmark, where we performed small 64-byte writes on our Intel server. And we can see here on the left-hand side that sequential writes actually scale pretty well with more threads, and they're very close to DRAM performance. But we can see on the right-hand side that random write performance drastically decreases very quickly compared to DRAM. And so a main fact here is that Optane persistent memory has a write combining buffer on the DIMM, so sequential writes can be combined efficiently, whereas random writes cannot. So this leads us basically to our first conclusion that direct sequential writes are okay to PMem, whilst random writes should be avoided. The second design choice we came up with is based on one of the characteristics of persistent memory, which is interleaving. So interleaved persistent memory has data striped across all available DIMMs, commonly in 4 kilobyte strides. So you can see here a 24 kilobyte range will be evenly distributed across all DIMMs. This is very similar to a RAID 0 configuration. And suddenly now alignment issues are relevant. So to investigate this, we ran a small benchmark with 4 kilobyte sequential writes, and we changed the offset and where we start to write. So if we have no offset, so we're aligned to the DIMMs, we can see a certain performance. And if we increase the offset, we can decrease performance by up to 20%, nearly up to 20%. So the offset where we write to actually makes a big difference. So this basically leads to our next conclusion, that we need page-aligned storage segments to fully utilize the underlying PMem hardware. The third design choice we looked at is commonly in databases, records are written to a log file. And if we have multiple threads writing to the same log file, this means that if we have small writes, they all write to the same DIMM. Whereas if we give each thread its own log file, we can evenly distribute this across all DIMMs to achieve higher parallelism. So the next benchmark we ran, we checked exactly this. You can see here for one, we only have one log file, and 32 would represent each thread has its individual log file. And we can see here again that when individual log files are used, we can achieve a lot lower latency in writes, very close compared to DRAM. This leads us to our third and final design choice, which is we need a uniform thread-to-DIMM distribution to achieve parallelism on the underlying hardware. So let's look at Viper, the key value store we built. And Viper, based on these design choices, we decided to build Viper in a hybrid design. So we have a volatile and a persistent storage part. We store a volatile offset map or hash index, which takes a lot of the random writes that we need to perform, and then we store persistent key value records in VPages, and we group these VPages into VBlocks, which we'll look into in a bit. So a VPage is basically structured like this. You can see it's 4 kilobyte in size. We have a bit of metadata at the beginning for locking. We have a set of slots. So these are fixed size slots here in this example, where we can write records to, and it's all tightly packed. And then we have a free slot bit set to indicate which slots are set. And this also allows us to delete records simply by flipping the bit in the bit set. So this layout covers 2 of our design choices already. First of all, as the VPage layout is aligned to 4 kilobyte, we cover the storage alignment here. And the second one is that we can write to each VPage sequentially. So we write through the slots in an increasing order, which allows the underlying DIM to combine writes that come in sequentially. So the third design choice we still need to cover is a uniform thread to DIM distribution. And so for this, we introduce a Viper client, which is a lightweight object for the users to interact with the database, through which they issue their requests. So here, in this example, we have 3 clients, and each of these clients owns their own VBlock. So they are assigned a VBlock by Viper, and they sequentially write through all the VPages in the VBlock, as you can see here. When a VBlock is full, then the client will request a new one from Viper. So this reduces a lot of synchronization overhead because this only needs to be done when a VBlock is full. And then it starts writing to the new location and updates its metadata accordingly. And basically through naturally evolving clients, this ensures a even distribution across all DIMMs instead of one central synchronization point. So let's look at some evaluation results now. In our evaluation here, we first prefill the databases with 100 million records, and then we perform another 100 million operations on them. The records have 16-byte keys and 200-byte values, and we compare Viper against numerous other systems, some of which are existing PMem-aware or hybrid PMem-aware index structures. Some are pure PMem key value stores, some are hybrid key value stores, and some are existing key value stores that have been ported to persistent memory. So here we can see for put performance, Viper scales very well and also significantly outperforms other systems. And this is mainly due to the fact that Viper benefits both from the random I/O performance of DRAM while inserting into the hash index, but also the sequential performance of PMem while sequentially writing the records to persistent storage. The other systems all have a lot of random writes to PMem, or write to a single location, which then does not exploit parallelism. We can see for get performance that Viper is on par or above with other systems here. And this is because mainly we have a random access to PMem, which is unavoidable if we have random gets. But we can see here that the put performance overall is a lot better, while the get performance is on par with existing systems. So the last benchmark we'll look at is the storage placement benchmark. So in this benchmark, we run with the same configuration as before. We run here Viper once unaligned. That means we shift the storage segments. Instead of them being aligned to the DIM boundaries, we shift them off with an offset of 2 kilobytes. And we can see that this already decreases performance by 11% when inserting records. And then we also run an experiment where everything is placed in PMem, so also the volatile index, and another version where everything is placed in DRAM. And we can see that Viper performs 3 times better than the PMem-only version. We can see we're kind of utilizing the random access performance of DRAM here efficiently, so that gives us a really big boost. And the DRAM-only version is only 1.6 times better than Viper. And we have to add here that obviously this then does not include persistence. So we're only losing a bit of performance for persistence, but we're kind of really gaining a lot through this hybrid approach. So yeah, thank you everyone for listening, and I really encourage you to check out our paper and code, as this talk did not cover everything. So in the paper, we also discuss a lot of details around crash consistency and recovery. We have a lot more benchmarks that cover some of our design choices. And we also discuss how to handle variable length records in Viper. So thank you for listening. And if you have any questions, please feel free to reach out.